So for today's lesson, we're going to go back and do that lesson that I had skipped over. We're going to do section 3.2. And it's on Rolle's theorem and the mean value theorem. I'm only going to focus on the mean value theorem. It's going to be actually a pretty short lesson. I didn't spell that right, did I? Not at all. Ignore the O. There we go. All right. So with the mean value theorem, this one, you're guaranteed to probably see one, maybe two questions like this one on the AP test that are going to utilize this theorem, that they won't necessarily ask you, or that they won't necessarily tell you this is what you're going to use. It's going to be probably a word problem, very likely in the last sections you do, the free response sections. Maybe you'll see something in the multiple choice, but I've usually seen it more in the free response. Usually one part of one problem. So the mean value theorem is pretty simple. If you want to look it up, it's on page 174 of your textbook. And it basically just says, if your function is continuous and differentiable, and we'll talk about what that means, on the interval from A to B, then there must exist a C value where the derivative at that value is equal to the slope of the points found from our interval. Wrote that differently than in the book. In the book, I think it's easier to see the equation in the book. I was trying to explain it. What this means ultimately is your change in your y's over your change in your x's, which you can write either way because with slope you'll get the same thing, of course, just as long as you're consistent about what comes first, a's or b's. So first of all, there are some important conditions in here you do have to check for before you're allowed to apply it. Continuous. You can't pick up your pencil while you're writing it, or whatever you're writing with. So in other words, if it's got an asymptote in there, in the interval, no good. If it just jumps some points, or it doesn't include all the points, like a square root has a certain starting point, doesn't count. If it's got a hole, doesn't count. It's got to be a continuous smooth function, and smooth here, that's where this comes into play, cannot have any sharp points. This function, or this theorem, just falls apart if either of those things are true. So we're being specific about they can't be true for this to happen. So ultimately, with a picture, this means if we have a function, just making up any old curve, and we're going to look at it from A to B, they're going to have some f of A and some f of B. And if I connect those two, there's going to be a slope from A to B, or B to A again, however you want to do it. The theorem is telling us by definition, somewhere in here, there's a tangent line that's parallel. At some C value, the derivative of my function, let's go ahead and plug in the C though, is going to equal the slope of MA to B, which means that they're not going to show up in the same place, but they are parallel. So again, not going to be super stressful about this lesson. It's a reason why I picked it for the last one before we go on holiday. But let's say that we have this function here. And we're going to be on the interval, and I'm just pulling an example from your book right now, from 1 to 4. This means that you're going to, first of all, you're going to want to find f of 1, and you're going to want to find f of 4, because we need those y values to find the rise and the run. So this would be 5 minus 4. And this one would be 5 minus 1. So my slope that I'm going to be paying attention to would be f of 4 minus f of 1 over 4 minus 1 to get that rise over the run. So let's see. F of 4 gave me 4. F of 1 gave me 1. And then over the bottom here, so I get 3 on top, 3 on bottom. I get 1 out. Now what it's wanting us to do is we want to find the place where our C value exists. So we know somewhere between 1 and 4, there is a point with a tangent line slope equal to 1. So I do this by tangent line slopes. You always find those with derivatives. So I'm going to take the derivative of my function. The 5 goes away. Let's write this, in fact, as f of x equals 5 minus 4 to x to the negative 1, just because it's easier to take the derivative when it looks like that. So I'm going to bring that down. This becomes plus 4x to the negative 2. In other words, 4 over x squared. And I'm going to take that equation, I'm going to set it equal to the slope that I know it's got to be parallel to. And I'm going to solve it for x squared. And on this, remember, when you take the square root, remember to do a plus or a minus. So I get x would equal positive 2 or negative 2. And because I'm looking at a specific interval, I only want one of those answers. And let me pull up Desmos, and we'll double check that problem. So I'm going to start by writing this off the screen, just because then I don't cover up my own work. So and I want this from, I'm going to put in my condition going from 1 to 4. Now, I'm not going to have the full equation here, because if I did, I'll have found so far it's a slope, so I haven't found the plus b part of it yet. But, well, let's see. I can't really annotate using what I have in front of me, but I want you to see here that if I were to connect the lines that are the endpoints, and if I were to draw in the tangent line right here, at x equals 2, those two lines will be parallel to each other. So you can use this for some fun word problems, and that's probably the most likely place you would see it. So for example, if you look at your book, and you look on page 175, there's a problem about somebody going past some police cars. And they tell us that we have these two police cars. They are stationed 5 miles apart from each other. And there's a car that passes them. And when they pass the first patrol car, they're going 55 miles per hour. And when they pass the second patrol car, they're going 50 miles per hour. And the problem says, prove they were speeding in the middle. And in the problem, it also tells us that the speed limit is 55 miles per hour here on this stretch of road. So we don't really necessarily have an equation here that we're going to take the derivative of. That's okay, though. What we're going to have is this idea that your average velocity is going to be, remember, that's just going to be your position divided by your time. And let's see, one thing I missed on when I wrote it down is it takes 4 minutes for him to get from one police car to the other police car. So, with your average velocity, your position over your time, we know that he had to have traveled 5 miles, and then the time is in minutes, but this is where you're going to be most likely to get tripped up. Because your units are in a different time measurement, you will want to do a conversion on this. And there are 60 minutes in 1 hour, so 4 over 60. Let's see, hours, which is 1/15 of an hour. You'll want to use that number here instead of the 4 minutes. Otherwise, the 4 minutes will throw you off completely. So we got a fraction over a fraction. You got to think about my little sister. We're going to take the first one, leave it alone. Take the second one, flip it upside down. And we get out 75. And this was miles. This was hours. Well, this was hours. Never mind, the whole thing. We're going to get 675 miles per hour. So all this proves is at some point between these two cars, we don't know where, we don't know when, but we can prove that somewhere along the line they had to have been going 75 miles per hour, according to what this theorem says. So, I'm leaving you a couple problems with the mean value theorem, just enough to expose you to it. Have fun with it. Should be pretty quick with meeting with your study groups. Let me know if you have any questions. And here we go. This is your last lesson before we go off on the break.